Still sticking with section 2.1, the next thing we're going to examine is what's called critical points of autonomous differential equations. The zeros of this function f are of special importance. We say that a real number c is a critical point of the autonomous differential equation if it makes the function f equal to 0. In other words, if you substitute f of c, if it gives a 0, then it's what we call a critical point. A critical point is also called an equilibrium point or a stationary point. We can observe that if we substitute the constant function y of x equals to c into this expression, so if we have a constant, then both sides of the equation would be 0, which means that if c is a critical point of this equation, then y of x equals to c is a constant solution of the autonomous differential equation. So we can find the constant solutions. Those are simply going to be given by the critical points of the function f of p, or in this case f of y. A constant solution y of x equals to c is called an equilibrium solution, and equilibria are the only constant solutions of 2. So if a solution is going to be constant, it's going to be one of these equilibrium ones, and those are the only constant solutions. As we already talked about before, we can tell when a non-constant solution, y equals to y of x, is increasing or decreasing based upon the sign of its derivative, dy dx. That's that function f of xy in general, or in this case we're looking at autonomous d's, so it would be simply f of y. Let's take a look at an example of one of these, and let's find some of our equilibrium solutions. Let's suppose we had the first order autonomous differential equation dp dt equals p times a minus b times p, where we're going to make the assumption that a and b are both positive constants. So this function p, we think of it as being a function of t. The independent variable t does not appear anywhere on that right hand side, so it is autonomous. Let's go ahead and find those equilibrium solutions. So the function f of t that we're talking about, it's this one right here. So f of p is going to be p times a minus bp. To find the critical points, we're going to set f of p equal to 0 and solve. So when is p times a minus bp equal to 0? Well, it's already factored, so you can set each factor equal to 0. We get p equals to 0, or a minus bp equals to 0. I can add the bp to both sides, divide by b, and we would get that p equals a over b. So we have two equilibrium solutions here. They are the following. So one is the constant function p of t equals to 0. The other constant solution, p of t, would be equal to a divided by b. So those are our two and only constant solutions for this differential equation. The next thing we want to do is let's also create the phase portrait for this. Okay. So the phase portrait, what we're going to do is we're going to plot those two numbers on a vertical axis. So this is going to be the p-axis. We have 0, which is here. We have a over b, which we know is above it because a and b are both positive constants. So this is some positive fraction. It's going to lie above it. And those two numbers break this vertical number line up into 1, 2, 3 different regions. Okay. Let's see if we can determine the sign of p within each region. Or actually, let's not determine the sign of p, let's determine the sign of f of p. to see what's going to be happening here. So again, we don't have exact values for this, but we can still kind of qualitatively go through and figure it out together. Let's take a look and see what's happening in region 1, the stuff that's below 0. So this, on the p-axis, if p is less than 0, then that means that this factor here would be negative. Now p is negative, so a times a negative b times a negative b times a p-value that's negative, that would make this thing on the inside a positive quantity. So we would get a negative times a positive, which means that f of p is going to end up being negative in the first region. So that means that it's going to be decreasing, so it would be heading down. Let's see if we can figure out what the sign of f of p would be in region 2. In region 2, we're between 0 and a over b. So now, if we're in region 2, first of all, p is going to be positive. So this first factor out in front is positive. And because p is kind of small in this region, this value here is going to be positive. How do I know that? Well, let's think about it like this. If I look at that factor, a minus bp, if I want to know when is it greater than 0, I can add bp to both sides, divide by b, which is a positive quantity, so it doesn't change the sign of this, and there's your answer. Okay. When a over b is greater than p, this factor is positive. So we have positive times positive, which means that f of p will have a positive sign, meaning it's greater than 0 in region 2. So if it's greater than 0, then that means that it's kind of acting up. So it's going to be increasing. And then lastly, let's see what's going to happen in region 3. Well, in region 3, these are values of p that are now bigger than a over b. So this first factor will still be positive, but now the second factor is going to end up being negative. Again, if this quantity is positive when a over b is bigger than p, then when p goes the other direction, then when p is greater than a over b, then this factor here will be negative, which means that f of p is going to be less than 0 in region 3, and if it's less than 0, it's decreasing, so it's going to be going down. And this will have some implications for the behavior of our solutions, our non-constant solutions, here in a little while. But just a kind of recap, we found our equilibrium solutions. You take the autonomous part of your differential equation, set it equal to 0. That allows us to find the equilibrium solutions, which were the constant solutions. From there, we went to do the phase portrait. We plot our solutions on a vertical scale, and then you went to determine the sign of f of p within each of those regions. This one was a bit more abstract because we actually didn't have a concrete function with concrete values a and b, and the ones that you'll have to do for WebAssign, you will have some concrete values here, so you could even do things like picking test points, like picking p-1, picking p as some fraction here, etc., plugging it in to see what the sign of f of p is. Unfortunately here we just had a and b. All we knew that they were both positive, but we could still qualitatively figure out the sign for f of p. So as we said a moment ago, here's our two constant solutions, 0 and a over b. It's going down or decreasing below 0. It's increasing between 0 and a over b, and it's decreasing above a over b. Okay, we're just going to simply refer to this as the phase portrait, and then the vertical line sometimes is referred to as the phase line. Without solving the ODE in this case, we can usually say a great deal about its solution curves. Since the function in 2 is independent of the variable x, we may consider f to be defined for all real numbers or for x greater than or equal to 0. And since f and its derivative f prime are continuous functions of y on some interval I of the y-axis, the fundamental theorem that held earlier in chapter 1 will hold in some horizontal strip R in the xy plane corresponding to I. So if we pick any point in that region, there will only be one solution curve that will pass through that point. Let's just suppose that this region has exactly two critical points. Let's call them C1 and C2, and we'll further make the assumption that C1 is less than C2. That means that our two equilibrious solutions would be y of x, the constant solution, equals to C1. We would have the other constant solution, y of x, equals to C2. Those two horizontal lines would divide the plane region up into three subregions, like this. So here's our first equilibrious solution. Here we have our second equilibrious solution. And then we have the three distinct regions that would be formed by them. We'd have the stuff that's below the two constant solutions, the region in between the two of them, and then we'd have region R3, which is the region above the two solutions. And now we make the following observations. Okay. So by continuity of f, so remember, those are the places where the function f is 0. And we're talking about the function f of y in this case. That means that the function f will have a consistent sign within each of these regions. So the sign of f will be consistent. In other words, it's always going to be either all positive or all negative in region 3. Likewise, f will be either all positive or all negative in region 2. And similarly, all positive or all negative in region 1. It's going to have a consistent sign throughout each region. So what this tells us is that the solution curve will stay within R2 for all x, because the graph of a non-constant solution cannot cross the graph of either equilibrious solution, y of x equals to C1, or y of x equals to C2. Since dy dx, which we're thinking of now as a function of y, it's either positive or negative in the subregions, the solutions that we get will be strictly monotonic, meaning that they will always be either strictly increasing or strictly decreasing within each subregion. Therefore, y of x cannot be oscillatory. You can't have it like bouncing up and down or back and forth. So nor can it have any relative extreme values for that matter. Remember, in order to have an extreme value going back to calculus 1, you would need to have a change in the sign of the derivative or a discontinuity, and we're not going to have that in this case. If y of x is bounded above by the critical point C1, where y of x is less than C1 for all values of x, then the graph of y of x must approach the graph of the equilibrious solution, y equals to C1, either as x approaches to positive infinity or as x approaches to negative infinity. If y of x is bounded, that is, if it's bounded above and below by two consecutive critical points, so if we're in that region 2, then the graph of y of x must approach the graphs of the equilibrium solutions, one as x approaches to positive infinity, and then the other one as x approaches to negative infinity. So if you're in this region 2, it's going to approach them in one way or another. So it's going to have to behave something like this. So either you're going to see solution curves kind of go like this in this nature, or the alternative is that it might go like this. Again, it's going to be monotonic, so it's going to be either all decreasing or all increasing, and it would have to approach the equilibrium solution, one at negative infinity and one at positive infinity. And you can figure out in which direction it would approach if you knew the sign of that function f of y in region 2. For example, if f of y was positive, in other words, the function solutions would have a positive rate of change, it'd be increasing, then it would look like this, because that would be a monotonically increasing function in region 2, in which case the function would approach c1 as x would approach negative infinity, and it would approach y of x equals to c2 as x approaches positive infinity. Conversely, if, let's say, y of x was less than 0, excuse me, f of y was less than 0, then it would go in the other direction. So then this would be representative of a function that was monotonically decreasing. So a decreasing solution curve would look something like this in here. In this case, it would approach c2 as x approaches negative infinity, and it would approach c1 as x approaches positive infinity. Let's go back and revisit example 3. We had the three intervals on the p-axis that were determined by our phase line and our critical points between 0 and a over b. So for us, region 1 was played by the role of negative infinity less than p less than 0. R2 was the region between 0 and a over b. And then region 3 would be the region that was above a over p. We already did the sign, the phase portrait for this. So if you recall that p was less than 0, and if p of t is bounded above, since p of t was decreasing, p of t decreases without bound for t increasing. And so p of t will approach 0 as t approaches negative infinity. This means that the negative t-axis, the graph of the equilibrium solution p of t equals to 0, is a horizontal asymptote for the solution curve. So remember, here was our phase plane. It was like this. Remember, it was decreasing, so it's going to be decreasing in region 1, which means if you look at what's going to happen as time approaches negative infinity, the curve will kind of go backwards. It's going to rise up, but again, it can't cross that equilibrium solution. So as t approaches negative infinity, then that solution curve is going to approach the equilibrium solution 0. What's going on in region 2? Well, in region 2, this is when p was between 0 and a over b. All in there that the sign of p of y was positive, so the solution was increasing, which means that if it's increasing, it's going to look like this. So as time approaches negative infinity, it's going to go back and approach the constant solution p equals to 0, and as time increases towards positive infinity, it's going to approach the constant solution a over b. So it's approaching 0 as time goes to negative infinity. It's approaching a over b as time goes to positive infinity. And then we could ask the question, well, what's going to happen in this third region? We already determined from our phase portrait that it was negative there for p, which means that it's going to be decreasing like this. So as t approaches positive infinity, the solution curve will approach a over b. So p of t approaches a over b as t approaches infinity, because it is bounded below.